Assalamu alaikum. We are group 4. Myself, Akar Dakal, ID 2022-03, and my group mate, SM Rakib Hassan, ID 222-41038. We are we are presenting chapter 6, the VC dimension from understanding machine learning by Saib and David. First, to understand what VC dimension, we need to understand what learnability means. A learning problem is said to be learnable if there exists an algorithm that can find a hypothesis with low error for a given hypothesis class and a sample of labeled data. The VC dimension of the hypothesis class is a key factor in determining the sample complexity and the generalization error of a learning algorithm. Hypothesis class may be of two types. They are finite hypothesis class and infinite hypothesis class. Finite hypothesis class are further of two types. They are pack learnable and agnostic pack learnable. Pack learnable or probably approximately correct learning is a framework for analyzing the sample complexity and generalization error of learning algorithms. A learning algorithm is packed if it can output a hypothesis with low error with high probability from a small sample of labeled data. The VC dimension of the hypothesis class determines the sample complexity and the generalization error of a pack learning algorithm. Moving on to agnostic pack learning. It is a variant of pack learning where the learner is not required to output a hypothesis from the given hypothesis class, but only a hypothesis with low error. The VC dimension of the hypothesis class still plays a crucial role in determining the sample complexity and the generalization error of an agnostic pack learning algorithm. Infinite hypothesis classes are also learnable. For this, we need to find the VC dimension of the hypothesis class. If the VC dimension is finite, then the class is learnable. There are some restrictions in the infinite hypothesis class. The number of independent vectors are the restriction in the hypothesis class. Each of the unique vector is called dichotomy. If all possible dichotomies from the sample classes are variable, then the hypothesis class shatters the sample class. Also, when there is shattering, there is no restriction. Shattering is the ability of a model to classify a set of points perfectly. More generally, the model can create a function that can divide the points into two distinct classes without overlapping. It is different from simple classification because it considers all possible combinations of labels upon those points. We simply define the VC dimension of a model as the size of the largest set of points that the model can shatter. Finally, to define VC dimension, also known as Vapnik-Cherkovitsky's dimension, is a model capacity measurement used in statistics and machine learning. It is termed informally as a measure of model's capacity. It is used frequently to guide the model selection process while developing machine learning applications. We need VC dimension to understand the trade-off between the expressiveness of hypothesis class and its ability to generalize to new data and to design and analyze learning algorithms that minimize the generalization error. Now, my friend Rakib will continue with the presentation.
Assalamu alaikum. I am SM Rakib Hassan, ID 222411038. Speaking of the applications of VC dimension, the VC dimension is used in theoretical analysis of machine learning algorithms. It provides insights into the trade-off between model complexity and generalization performance. Also, it can be used to compare the expressiveness of different hypothesis classes. Furthermore, it can be used to design and analyze learning algorithms in various domains, including computer vision, natural language processing, and robotics. So from VC dimension, we can derive different types of bounds, which can help us understand the characteristics of the hypothesis class. They are the upper bounds, lower bounds, and combining both of those, we have the generalization bound. So upper bounds are various methods for bounding the VC dimension of a hypothesis class. For example, the combinatorial, geometric, and probabilistic methods. A tight upper bound on the VC dimension can help design efficient learning algorithms and avoid overfitting. For lower bounds, the results that show the minimum VC dimension required to shatter certain sets of points. For example, Searle's lemma, the combinatorial lemma. A lower bound on the VC dimension can help prove the hardness of learning certain problems. Speaking of Searle's lemma, it is a mathematical result in machine learning that helps us understand the complexity of a hypothesis class, which is a set of possible solutions that a learning algorithm can choose from. Searle's lemma helps us understand the capacity of a hypothesis class to fit the data, which is important for designing and analyzing learning algorithms. It is also used to prove lower bounds on the VC dimension, which is a measure of the capacity of a hypothesis class to overfit or generalize. Another important topic is no freelance theorem. It is a fundamental concept in machine learning that states that, on average, no algorithm can outperform any other algorithm when considering all possible problems. This means that no algorithm is universally better than another one for all possible learning problems. No-frills theorem and the VC dimension are related in the sense that they both emphasize the importance of understanding the problem-specific characteristics of the data when choosing a hypothesis class or a learning algorithm. The no-freelance theorem implies that there is no universally optimal hypothesis class or learning algorithm, while the VC dimension provides a way to quantify the capacity of a hypothesis class to fit the data and generalize to new unseen data. Together, these concepts highlight the need to carefully consider the problem-specific characteristics of the data when designing and selecting learning algorithms. So for growth function, it is a function that counts the maximum number of distinct dichotomies that can be generated by a hypothesis class on a set of endpoints. It can be used to compute the VC dimension. Last but not the least, I am talking about some common VC dimension of hypothesis. So for all threshold functions, the VC dimension is 1. For all convex d-gons, the VC dimension is 2d plus 1. For all hyperplanes in d dimension, the VC dimension is d plus 1. For all axis-aligned rectangles, the VC dimension is 4. And at last, for all interval functions, the VC dimension is 2. That is all from our side. Thank you for your patience. Assalamu alaikum.